Hello, good afternoon. This is Ms. Chambers. I'm so glad that you could all join us for this talk we have for today. Before we get started, I have a few announcements. We have disabled the chat window. This is so you can save your questions for the end, and we'll go over that on how that process will work for questions. So we're so glad you could join us this afternoon. Before we get started, I want to introduce, we have a few guests online, and they're going to talk to you for just a second. We have Fred Kepner from Marshall Space Flight Center online today, and if you're selected to go to Marshall Space Flight Center, you'll actually get to meet him. So Fred, would you like to say hello? Maybe he stepped away for a second. So our next person is Alicia Badaroni-Cortez, and she is the program manager for NCAS, and you've probably seen her in the NCAS Cafe chatting with you guys.
Hi everybody, I just want to say hello and welcome to chat number 2. We've got a fantastic guest lined up for you, and we're really amazed at all of the work that we see you doing and the quizzes that you're passing and all the comments in the NCAS Cafe. You guys are just, you're killing it, and we're really impressed with you. And so I just want to give you a little words of encouragement to keep up the good work, and we hope to see you all finish so that we can extend an invitation to you to come either here at Johnson, over at Marshall, or at JPL. So I'll turn things back over to Maria.
All right. Welcome. We're so glad you could join us. All right, looks like Rosalind Soto has joined us from the Jet Propulsion Laboratory in California, and if you're selected to go to the Jet Propulsion Laboratory, you'll get to meet Rosalind and her team. So Rosalind, if you have a camera or a microphone, if you would like to say hello. And Fred, if you would like to say hello as well. I just got your message. Oh, Fred, you'll need to turn your microphone on so we can hear you.
Gotcha, thank you.
Push the talk button.
Can you hear me now?
It's underneath your picture.
I hit it. Can you hear me? Can you hear me?
Yes. I can hear him now. Fred?
Oh, you got me now? Okay.
Yes, I got you.
Well, thank you. It was pressed. I'm not sure what's going on. But my name is Fred Kepner. I'm here at Marshall Space Flight Center in Huntsville, Alabama, and I'm glad to be able to participate in this and look forward to it. So thank you very much for inviting me.
All right. Well, we're excited you're here. All right. Rosalind, do you have a camera? Okay, that's all right. Well, we're excited that you're here for the chat this afternoon, so we welcome you. All right, so now we're going to get started. We're going to go ahead. I'm going to introduce our speaker for today. Our speaker is Aaron Herridge, and he is working on finishing his degree in physics, but he's also working with Aries studying and researching Mars geology. So he is an expert in this field, and he's going to tell you all about Mars geology today. So we welcome you, Aaron.
All right. Hello, everybody. My name is Aaron. Thank you, Maria, for the great introduction. So I'm going to talk to you all a little bit about what's going on and below the surface of Mars. I understand that you're going to be designing some exciting mission plans. So I'm going to give you information that I believe will help you design those plans. But at the end of the training, you'll get a chance to ask me questions if you have anything that you're specifically wanting to hear more about. So with that said, I'm going to go forward. A little bit about my background, if you haven't looked at my bio yet. I have completed a geology degree at the University of Houston Clear Lake, and I'm currently working on a second degree in physics that I will be finishing in December 2015. I'm also doing ongoing research in fluvial dynamic work in Sinus Meridiani, which is on Mars, and I will tell you a little bit about that area in just a bit. It's pretty exciting. And I've worked on a few other areas of research. electromagnetism, astrophysics, and some atmospheric chemistry. So just a few different tools that I bring whenever I'm looking at Mars that have helped quite a bit. I've also been an intern twice here at Johnson Space Center, and that was in 2013. I worked on the very same work in Mars geoscience that I'm studying still today. So if you have questions about my internship experience, if you're looking at an internship, definitely feel free to ask me, and I will reserve that for later. So introducing planet Mars. We've all seen pictures of Mars. The image that you see on your screen right now is probably not very new to you. It's a very detailed image. But we're going to zoom into a few areas around Mars so that you have an idea which locations are doing what. Because from one area of Mars to the next, there's a lot of very different things that are happening. And when you're looking at designing landing missions, some places may be of more interest to you than others, so I'm going to make sure that you understand what the differences are. Just a little bit of a zoom out first. Mars's position in the solar system. It's a little basic, but just so that I can tie this in, we know that Mars is positioned between Earth and between Jupiter as far as the orbital distance from the Sun. And between Mars and Jupiter is the asteroid belt. Now, it's probably not new to all of you, but keep that in consideration when you're looking at Mars surface features, because that asteroid belt there, you'll notice that Mars is between Earth and that asteroid belt. Because of that, there's a lot more impact events that occur on Mars than occur on Earth. You can already look at the moon of Earth and see that if Earth didn't have all this weathering and erosion and atmosphere, we might have a different looking surface. And Mars has a lot of different features on its surface where in some places you see lots of craters, there's been lots of impacts, and others look as smooth as what places on Earth do. So that's a part of understanding the history of Mars, and that's a part of understanding where you want to look at on Mars if you're looking for particular missions. So keep the asteroid belt in mind when we're talking about landing missions. As far as just a physical description of Mars, it's got some very odd characteristics. It's got a mass that is almost a tenth of the mass of Earth, but the diameter of Mars is only about half of Earth's diameter. So you can see that Mars has a lot less of a mass per area ratio than Earth does. Now we know that Earth has a pretty solid iron core, and it's got a lot of heavy elements inside of it. So while we don't know a lot of detail yet about the interior of Mars, we do know that it has a lot less mass inside. So when we're looking at Mars and we're looking for places to study, those are some questions that right now scientists are really trying to get to the bottom of. And while there's some missions that are being planned in the future to get more info, you may want to plan a mission that seeks to understand the interior of Mars better, because it is still a mystery to us. Talking about the internal structure of Mars, I'll go over what we know and what we suspect. What we know is that Mars has some sort of a semi-fluidic core, not unlike Earth. And that iron, nickel, and sulfur are a part of that core, also not unlike Earth. We also know that Mars has a silicate mantle that is believed to be mostly dormant compared to Earth. Not as much evidence of active tectonic activity. So how do we know that? I'll talk a little bit about that later, but when we're looking at meteorites that have landed on Earth and we've been able to determine that they're from Mars, there are some meteorites that we believe are from the mantle of Mars, so we believe we're getting an inside look at it. Mars has a thicker crust than Earth's by ratio, and the crust of Mars is composed largely of iron, magnesium, aluminum, calcium, and potassium. Iron is of particular interest because we all know Mars to be that red star in the sky, and when we look at the planet's surface, we see so much red, and if you wonder about that, iron is really the key to that. And it's also a key to what you're going to be looking at within your rovers that are investigating the surface. You know, why is there so much iron, and what is the iron doing? The smaller core that Mars has compared to Earth, I hinted at this earlier, it's got significantly less mass. So when you have a significantly lower mass iron core in a planet, that has a direct impact on the magnetic field that the planet is capable of producing. Mars has extremely weak evidence of magnetic field. And that can have an impact also on the geology, if you can believe it or not. The lower magnetic field, it actually does relate to things going on in the atmosphere, which is also relevant to what we see on the surface. So I'll talk a little bit more about that later as well. And of course, obviously, you know that with a lower mass core and with a lower magnetic field, lower gravity is also going to be a part of that. So just like on the moon where you can bounce pretty high if you jump, Mars, you definitely have a lot less weight pulling you down than you do on Earth. So a little bit about the history of Mars. This is important when you're investigating geology on Mars. If you've ever gone to the Grand Canyon on Earth, or if you've seen pictures of it, you know that if you dig a hole deep enough, you're going to see different layers or different strata that come from different periods of a planet's history. And Mars is no different. It also has different periods of history, and if we were to dig deep enough, we would see strata that tell us a little bit about those periods. Indeed, we have seen at least a little bit from space of some strata on Mars. Not in great detail, we'd love to see more of that, but what we can see is that there are about 4 major periods to the history of Mars. There is the pre-Noachian period, which is the first period, and that is a period when, if Mars ever had an atmosphere, it probably wasn't there yet by then. So there wasn't much protecting it, and as you can imagine, the early solar system being a place with lots of bouncing meteorites, Mars took a lot of craters during that period. So a lot of the craters that we see today, believe it or not, were formed early in Mars's history. So that's important to know, because when you're looking at features on the surface and you want to know more about them, you should probably know what period they're from and what kinds of things that you're going to find if you look there. Following the pre-Noachian period, the Noachian period itself also continued to have a lot of craterization occurring, but at the end of this period we start to see evidence of what could be water. There's some weathering, there's some deposition, and while there's ongoing debate about what causes the deposition and the weathering, water is one of the possible suspects. So if you're really interested in the story of water on Mars, if there was a lot of water, that's probably one of those strata you'd like to find. Following the Noachian period is the Hesperian period. And this period is also a period where we see things that could be possible water, but we do know that there's a lot of lava plains that formed during this period. So for those of you who are interested more in investigating volcanic activity on Mars, you're going to be interested in places where the Hesperian period strata is exposed to the surface. Lava plains are pretty easy to spot on a planet because where you should see craters, you see a lot of smooth surface. When you look at the moon and you look at those beautiful smooth mare, you're seeing lava plains that formed a long time ago and then they cooled quickly into a smooth surface, and they just haven't had a lot of craterization since then, especially since most of the impacts in the solar system are just from the very beginning of the solar system's history. So when you're looking at lava plains on Mars or smooth surface features, be aware that the Hesperian period is a period they probably formed, and again, lava is the strongest suspect at all times. All right, the final and most recent period in Mars's history is the Amazonian period. And that is the period that continues to the present. And the Amazonian period is marked by a pretty wide variety of surface features, partly because things going on in this period are actually excavating and uncovering those earlier periods. So you can see a real mix of surface features where we're looking at the Amazonian period. Some features that formed during this period include, believe it or not, Olympus Mons, the mountain on Mars that has the distinction of being the largest mountain in the entire solar system. Many of the lava plains are still being formed during the Amazonian period, even though the bigger period was the Hesperian period. However, if water existed extantly on Mars's surface, we don't see a lot of evidence during Amazonian period strata and Amazonian period excavations. So keep that in mind if you're really interested in water. And there are some impact craters in the most recent period. In fact, it's really cool. We have seen new craters formed from time to time, very small ones, because we have so many eyes on Mars now with all of the instruments that we've sent over there. So that's the Amazonian period. It's very ranging in what it includes, but water is not the big story so much with that period. There are a few other interesting things that I will talk about later, though, that you can see going on today. If you're not familiar with Mars geography and place names and locations, I'm going to give you just a quick tutorial on that. You're looking at both, if you will, both sides of Mars, if there were sides, and a number of place names that are very significant that cover the biggest areas. So right off the bat, if you look on the right-hand side of your screen, you'll see Vastistas Borealis, which is that very large, smooth plain across almost the entire northern third of Mars. We don't know today what caused that smooth surface, but it's very unusual. We don't see something like that very often. That's something you would see underneath, say, the Pacific Ocean on Earth. Also, on the Moon, there's some pretty large mares that have been formed, and it might be similar to that, but these are very large. They cover a very large area. So there's a lot of scientists who really want to know what happened to cause that feature. Was it an ancient ocean? Was it an enormous impact event that occurred a long time ago that liquefied the crust at the time? Or could it have been a lot of volcanic activity going on at one point in Mars's history? We just don't know. But that's one area of great interest that has not had a lot of investigation. Another place that has some interest for people who are looking for ancient oceans, look at the bottom of the right-hand side and you will see Hellas Planitia, that big dark blue crater in the image. And here I should specify, if you didn't already see the scale at the bottom, the color shading represents altitude. So that dark blue crater looking area, that's very low altitude. That's the lowest area on Mars's surface. So the Hellas Planitia is another area that some people suspect could have been an ancient sea, especially since you have highland moving to lowland into a bowl-shaped feature there all around. So if Mars had rain a long time ago, it makes sense that water would collect in that area. This is also a location that has had virtually no surface investigation. I'll just briefly go over some of the other locations. If you look to the left, you'll see Valles Marineris, which is that big scar going across the Martian equator zone. That is a huge valley and canyon system, even more magnificent than the Grand Canyon on Earth. It's another question mark. We still don't know exactly how that was created. That is something a lot of scientists want to further investigate. Now, it's not necessarily where a lot of the water people are trying to focus on, because what we see there doesn't look as much like water features. That being said, it is a low area of elevation surrounded by high areas of elevation. Whenever you have that combination, if there's rain in the atmosphere falling down on the planet, water will collect. So if you could get into the canyon, you could probably find evidence of ancient water if it did exist on the surface. But even if you weren't interested in water, this area has a lot of exposed strata. So if you'd really like to just investigate what was going on in the different periods of Mars's history, that's one of the better places on the planet to see that. We haven't had any missions there yet, and that's partly because the terrain's very difficult to land on. So it's not the easiest place to drop a lander, and it's definitely not the cheapest place to drop a lander. So when you're designing missions on a budget, keep that in mind. Some of the exciting spots on the surface may be a little bit out of budget range. You can see Olympus Mons also on the left-hand side of that image. There are definitely people who want to investigate that further. Was it an ancient volcano that was depositing a number of materials around it? We don't know exactly what it's done in its history, but it's some place that a lot of scientists want to study further. But I include it mostly because it's a very good place marker. If you don't know geography on Mars too well, if you're still new to that, then Olympus Mons is always a good place to get your bearings straight. So if you look at Olympus Mons, you know that over to the left you're going into Vastistas Borealis, and that big area of open, smooth surface. And you know that to the right you have a lot of Mars's highest elevation terrain, and so you can use that as a place marker. And some of these other spots I'm going to talk about as I zoom in, so bear with me on that. So let's go into the geological exploration of Mars to date. I'm not going to go too much into these missions because you've already gotten a preview of it, but I do want to at least tie the timeline together for you all. So one of the first major instruments that was sent to Mars that gathered a lot of data for us was the Mars Express orbiter that was launched in 2001, and that actually featured infrared mineralogical mapping, something that the Viking landers definitely did not have with them. Since that mission and throughout the other ongoing missions that we've had, we've been getting a lot more clues about what kind of minerals are in the Martian surface. It's very important if we want to know what kind of world Mars was, or what kind of world we might want to make Mars into in the future. So this was an important mission, and on the right-hand side of your screen you can see an example of some of the kind of visualizations that mission was able to give us. I'm going to go right along here. The Mars Reconnaissance Orbiter, another very important mission launched in 2005. We got even more detailed spectroscopy from this mission, to where we got even more detail on the mineralogy of the surface. In fact, actually, if you look at the scientific literature that's been published on Mars surface geology, this is where you start to get some of the earliest data on actual large areas of certain mineral compositions. So you'll see this being referenced a lot if you look at peer-published materials, which feeds into the Mars exploration rovers, including Opportunity, which I've got on the screen right now, with a couple of photos of what Opportunity has seen. Opportunity is very interesting because it's the one of the two rovers that were launched in 2003 that's still running, much to everyone's surprise. And I'll talk about why that's important to you all in your designs. It had a twin, Spirit, which no longer is functioning. However, both they far surpassed the date that they were expected to go. These rovers were based on a solar power plan, and there were worries that since Mars has a lot of loose dust on the surface, that would coat and collect on the solar panels, and especially during the wintertime when light is dimmer across the entire surface of Mars, these rovers might have a hard time. And indeed, every winter they always had to do lower energy modes and lower energy states. That's definitely true. But Opportunity is still going today, much to everyone's amazement, which just goes to show that solar power can be a surprisingly affordable lander and rover option for you, and it's against everyone's imagination working quite well today to the surface. And with a small rover, you can still zoom in and get very good detail on the composition of the materials and the minerals that are on the surface. And we're going to see some great data that Opportunity has given us to show how a relatively affordable mission can give you a lot of value. And the Mars Odyssey orbiter, launched in 2001, has given us a lot of thermal imaging that has been very valuable to studying the surface of Mars. And the reason that is important is because from daytime to nighttime, certain minerals, when they're prominent in a given area of the surface, they're going to release heat or they're going to absorb heat, depending on what kind of minerals they are. This was an orbiter that was able to actually tell us what kind of minerals are probably present in parts of Mars based on thermal emissions. Now, we're not looking at this necessarily for rovers that are being designed to send to the surface, but it has given us some clues on where we might want to send those rovers. And of course, I think everyone's probably, especially lately, heard all about Mars Science Laboratory, or Curiosity. Curiosity is unique in the rover catalog because unlike previous rovers, it includes a nuclear-powered battery in addition to solar power and other forms of power that are capable and available to Mars rovers. Curiosity is going today. It's in the area of Gale Crater, and I'll talk a little bit more about why that's a useful kind of location to send a mission to. It's given us a lot of valuable data, And as you can see on the right-hand side of your screen, this is among the most beautiful close-ups we've seen of the surface from any rover. Not just rocks on the ground, but actual hills. And as you can see with those arrows, you can see what look to be exposed strata. So the Curiosity rover is just getting into its most exciting phase yet, where it's going to start to go up the hill over the next year or two. And we should see those strata up close and get a lot more information about what happened in the different periods of the history of Mars. So now that I've briefly mentioned these rover missions that you already probably are aware of, here's a map to give you an idea where they've been. And this is also going to be useful for you. Now you notice there's one up there that I didn't mention, and that's the Phoenix lander. That wasn't a rover. That was a stationary landing mission where it dropped a lander payload onto the surface and conducted investigations as close as possible to the northern Martian pole. At this time, with the budgets that we're working with, that's about as close as we've been able to get and probably could get. You'll notice that the rest of the missions on this map are closer to the equator. That's because the rover missions are trying to maximize the sunlight that they have, not only so that you can get good photographic imagery, but also because the Martian winters are not friendly to rovers. Not only if there's a solar-powered device, but also the fact that when it cools and the winds become stronger, it does make things harder on the instruments of the rovers. And the Phoenix lander is an example that if you get far enough close to that northern pole, you can only really have a mission for a few months before the payload equipment is going to no longer be functionable. However, if you do have a large budget and you can design a more expensive mission, maybe with a nuclear battery, like what Curiosity has, then getting close to the pole could be an option. But you will notice more missions closer to the equator. You'll also notice that they're not so much in the rugged terrain. So we really haven't tried to get too much into these canyons and valleys, nor have we tried to drop anything really as much in the middle of a large area of plains. We're looking for areas lately that show some terrain change, like crater rims or hill slopes, like Curiosity, what it's investigating. Even Opportunity has had some areas it's been able to look at, but gentle enough that the rover can actually get around. So with that, I'm going to go into some close-up imagery of Mars, and I'm just going to give you a little bit of an idea what you're looking at. And this way you'll get an idea, when you're looking at Mars, what is it that you're looking at, and is it valuable to you or not? Because different scientists are looking for different kinds of information. So to start out with, we're looking at a crater. At the bottom of the crater, inside, you see what look like dunes. On Earth, we would think that those were sand dunes, and you could run through them and throw the sand around in the air. But on Mars, that's not always the case. These sand dunes are concreted, so they're really solid. If you were to try to grab a chunk of that and pick it up with your hand, you might be a little disappointed. It's very cemented together. It's old, it's ancient, but it did, as you can see, deposit from the sides of the crater. You can actually see the trails that the sands were taking in the ancient past. You can still see that on the crater edge. Now, for some scientists, if they're studying, for instance, the aeolian deposit activity on Mars, which is the wind-carried sand deposition, they might be very interested in this feature. But if you're looking for, say, evidence of water, this is probably not a spot you're interested in. So when you're looking at craters that you might want to do a mission in, keep in mind what you're looking at. This would be a crater you would investigate if you're interested in sand and wind deposition in the ancient past. Here's another image that is kind of interesting. Again, this would be more interesting to a scientist who's looking at aeolian deposits. However, you're looking at two different things going on here. You do have sand, and again, cemented sand dunes in this picture. You can see those sort of tan beige, very small dunes that are on the surface there. But do you see those darker colors? Those darker colors in the sand are coming out in the imagery because the Martian soil profile includes, in certain places, a lot of CO2 deposits in solid form, or dry ice. So whenever we're looking for water on Mars and we see things that look like ice, sometimes what we're finding is dry ice, which is just frozen carbon. Now, CO2 doesn't go through the same phase change as water does. It's not liquid solid gas. It's just solid gas, at least at the temperatures at this part of the solar system. So what you're looking at here are either solid dry ice particles that are frozen and mixed in with the sand, or, as happens during certain seasons on Mars, they could actually be deposits of dry ice that are in the process of subliming, in which they're going directly from solid to gas, and they're moving through the soil or the sand looking for a place to escape into the atmosphere. So this is very interesting to some scientists who are really trying to better understand the story of ice on Mars, and they're not necessarily needing that ice to be water ice. This is also interesting because dry ice is probably the most dominant major thing that you could sit on the surface of Mars and watch happening today. There are actually geysers that pop up out of the surface because of dry ice that's turning into gas, putting pressure on the soil above it, and it's just escaping through fissures. So for some geologists, that's a lot more interesting than looking around trying to find evidence of water where there may not be any. So keep in mind when you look at that dark sand, for some scientists, there's some more. That's very interesting to them. Now this image it has something that the previous images didn't have. Notice that stepped elevation change that you see from ridge to plains below. So the darker soil below, you'll notice that cakes over some of those steps. That's because it was deposited after those steps existed. And those steps, if you look at them, they do look like they're pretty ancient. I mean, they're a little worn and weathered. So this would be a very interesting place to look for the story of water on Mars, because we don't know what made those step formations, but we can tell that it's been weathered. And those don't look like typical Aeolian weathering patterns, which would be the wind and the sand. This looks more like something that was fluid, was deposited in ancient times and solidified. So this would be an area that you might want to look at. Also, it is exposing strata. So if you had a rover on Mars that was getting a close-up look at this, you could actually see what kind of strata we're looking at and find out what period of history this is for Mars. And you could see what minerals were being associated with that point in history. So this would be a very interesting place. And because I've done research in this area, I'll give you a little bit of an idea of what probably happened in this location, because you're going to see it in other places that you really want to look for water. So here, probably what we had was a long time ago, there were crater features from the early bombardment period of Mars. And then over time, something on the surface was experiencing weathering. Not sure what was causing the weathering, but something was causing weathering. And these stepped features occurred at that time. But over time, they were probably reburied by sediments being blown around on Mars' surface by all the winds. So they were probably recovered up, and then in more recent periods of time, they've been uncovered again as the wind continues to circle that sand around the planet. So you probably have a feature here that was buried, and it's been relatively recently re-excavated. So you're looking at sediments there, that dark material that's very young compared to what you're seeing in those stepped features. So this is a place that would have a lot of history. It's not just good for looking for water evidence, but it's good just for understanding the story of deposition on Mars. Here's another interesting feature. Now, as I've been telling you, that darker material in the surface is often evidence of dry ice. These little slug-looking features here, scientists have been looking over them, and what they believe is happening is that this is actual pockets of dry ice in the process of subliming, trying to convert from its solid phase back to its gas phase. And so it's putting pressure on the surface above it and forming these slug formations or features. And you can see lots of loose rocks that have been pushed away from those slug features all across the ground there. So those are not on top of the slug features, it's because they have been pushed off. These features might have formed relatively quickly. And actually, if you look at features like this, a lot of times what you'll find are fissures that are developed, and you'll actually see geysers erupting with that dry ice that's venting out and becoming gas again and getting into the atmosphere. So this is a very interesting location if you're really curious about active geology, if you're looking for things happening on the surface today. And if we were to, say, settle Mars and we were to settle in an area near this, this would be very interesting to people because, well, if you built a little home on that, it would be, you know, pushed around. So you want to know what's going on the surface just like you do on Earth, and that is one of the more interesting things we're studying today. And then I threw this picture in. Some of you may have seen this in the news when it happened, but this is actually a tornado or a twister. It's a small twister that was actually imaged from space moving across the Martian surface. And that's because Mars does have an atmosphere. We may not talk about it like that, but Mars does have an atmosphere today. It's just a lot thinner, and it doesn't include a lot of the same kind of chemical compounds that Earth has. But it still has an atmosphere. It still has winds, and you still have weather patterns and phenomena that occur, like hailstorms in the northern polar cap, or tornadoes like this one closer to the equator or across the plains. And I'll tell you another interesting story about this image, or something that it relates to, is that the Curiosity rover actually at one point, it's got a wind detector on it, and it can determine wind moving around it and what direction the wind is coming from and blowing towards. And one day, when there were heavy winds around Curiosity, scientists observed that the wind patterns were circulating over the rover, and for a period of time it experienced high winds that passed in a split second. And so they actually believe that one of these twisters like this went right over the rover. Now Curiosity is about the size of a car, and it's moving with a nuclear battery, so it's pretty tough and it can handle that. But if you have a tiny rover, like something smaller than Opportunity, like one of the early rovers we sent to Mars, you might want to account for these wind features that occur. It could get blown around. Especially if you have a rover that goes missing, you don't know what happened to it. There's a lot of things going on the surface of Mars. One more thing to account for. All right. Commonly proposed depositional environments of Mars. I know that's a mouthful, so I'm going to break that down for you. If you're looking at geology on Mars, you want to understand what created the features you're looking at and the materials that made it. Where did they go after that? And what process is still going on today that's affecting that? Has it changed? So these are a list of the different types of processes that can deposit material in a new place on the surface. I told you about aeolian, which is wind taking materials, picking them up, and moving them to another location. When that happens, it's possible for sand dunes to cement, like I talked about earlier. It's possible for features that are rocky outcrops, for instance, to be broken down and weathered. It's also possible for sand dunes to form even today. And yes, today you can still find typical sand dunes like on Earth that are just moving around across the surface. So that's aeolian deposition. There's volcanic deposition. I think you probably know a lot about that already, so I won't go into that, but it's just volcanic activity on Mars. So there's lava and there's ash falling down, and those are things that deposit. There's fluvial activity, which I do in my research. That is where you've had either water that's causing minerals to cement together, or you have evidence of water carving features out of the surface, or even carrying materials from one place to another, which is something, by the way, that lava can also do. So you do have to be very careful when you're trying to rule out fluvial versus volcanic. There's lacustrine, which is, you can see LAC, it sounds like lake. It's lake formation features. And these are features that Curiosity has looked at recently, actually. You'll see flat deposits. You'll see very small dunes. I don't mean like a few feet, I mean like centimeters. And you may find mud cracks that are ancient mud cracks, and you'll find certain types of minerals, which I'll talk about a little bit later, that form in still water environments where there hasn't been water moving around, slushing around in waves. So lacustrine is an environment we have proven existed on Mars. We know there were lakes at one point, and we know that the craters were a popular spot for lakes to sit around. Atmospheric dustfall. On a planet like Mars, that's a big deal. It's not as much of a big deal on Earth. We do have the Sahara Desert, and it does have sand that gets picked up and carried off and deposited elsewhere. The Bahamas, a lot of the beautiful sand beaches there and the beautiful waters were created because of the Sahara Desert having sand moved over there across the ocean. Well, Mars had that on a much bigger scale. So when you're looking at features, you could find features that actually accumulated as dust that's suspended up in the atmosphere, just eventually kind of settles down in various areas of Mars. But one way that you can rule that out or determine if that occurred is that if you have atmospheric dust accumulation, you shouldn't see that accumulation has any relation to elevation changes. All right, it should be more evenly distributed. So if you find deposition that occurred because you have high elevation to low elevation, that's more likely water or lava. That's not as likely to be atmospheric dust fall. So again, that's one thing that can create sand dunes and can create deposits, and you have to rule that out. And finally, impact features. That is a source of deposition. When a meteor slams into a planet, not only does it carve out the crater, but it kicks up materials into the sky. And those materials deposit around that crater, sometimes for great distances. And those materials that it's depositing tend to be materials that were below the ground already, that were very deep, and that they got excavated. An example of what I mean by that is that on Earth today, if you go to some of the craters that we can go to, you'll find a lot of iron close to the crater rim. That's because that iron is common farther below the surface, and it was excavated out. So when you're looking at minerals that a rover is looking at on the planet's surface, you can determine if maybe there's a hidden impact, a hidden crater that's been buried, by just looking if you're getting closer to a field of iron that's going from higher concentration to lower concentration. Also, a crater rim that's partially buried can look suspiciously like a canyon or a water channel. So if you're looking for water, these can be deceptive. You have to rule out crater rims that have been partially buried. So that's very important if you're trying to design a mission to a feature that you want to find water around. All right, so now that we've talked about deposition, I'm going to go into the mineralogy on Mars. And this is going to be the type of minerals that you find on Mars today, and which ones might be of interest based on the mission you're planning. So the soil composition is very unique on Mars. It's not at all like what you see on Earth on the top layer. We know that Mars is the quote-unquote red planet. When you look at it from Earth, it looks very red. You get closer, it still has a very reddish-brown look. And that's not something that you see anywhere else in the solar system. And it's also not something that you see on Earth. And that is because Mars has a lot of oxidization that has occurred on the surface. It has a lot of iron that's been exposed to oxygen at some point in time. And that creates literal rust. So when you're looking at the surface of Mars, this is rust. You're looking at a lot of rust, which is important if you're looking at settling Mars, because rust is not safe for humans to consume. So you have to actually take steps to keep rust or that red material away from internal human habitats. It's also something that can be a problem for rovers. Rust is not good on metal, and this particular type of soil has, not unlike the moon, has a lot of sharp, fine edges to it. It's not like the muddy soil on Earth where you could pick it up with your hands and it would be safe to squish in your hands. This stuff could actually cut through materials. So it's actually a threat to the rovers. When it's blowing across the rovers, it is constantly wearing down on the rovers. So the rovers have to be made of very strong materials to resist all of this rust. Now what that rust tells us, since it's been oxidized, is that you're looking at a lot of materials that might have had some interaction with water at some point in time. So that is actually a curious feature in itself. It's slightly alkaline. So again, it's not exactly something you'd want to drink water out of. And if you actually get a scoopful of it and you look at what kind of minerals are in there, magnesium, sodium, potassium, and chlorine are some of the common minerals that you will see. There's also evidence that there's some salt perchlorate traces in there too. And salt's always interesting to find because salt frequently will lead you to water. soil recently shown to be similar to volcanic basalt sand in Hawaii. Recently, there was a very good analysis done by Curiosity on the soil, and a lot of the composition is similar to if you go to a volcanic sand beach in Hawaii. So if you're wondering kind of what type of materials are in there and what that's like on Earth, that would be a good comparison. I already told you what the red color comes from, and of course, since this is rust, this tells you there's a lot of iron in the surface soil of Mars. Now, iron's not the only thing that Mars has in abundance. This is a list of some of the common minerals that are on Mars and what they mean. I've got pictures on the right-hand side so you can kind of see some zoomed-in features of those materials. So hematite is one of the most common minerals on Mars. Hematite can occur anywhere, but there's certain types of hematite that are evidence that water has gone through them. And so when we're looking at the hematite on Mars, this red hematite, this is something that has a lot of interest in terms of water activity. Magnesium is fairly common on Mars. Olivine is fairly common on Mars. Those can be related to lava. They can be related to water. There's also phyllosilicates and salts, feldspar and basalt, again, common things. And there's also a very rare mineral called titanomagnetite. So these are just some of the things that you'll find. They suggest that Mars has had volcanic activity, some water activity, and some places the water activity would be flowing, and some places it would be stationary. So I'm going to take a moment right now and ask if there's anybody who would like to ask any questions on what I've covered to this point.
Can you share your screen? Can they raise their hands?
Give me 1 second. Just going to make sure that it's set up for you to be able to ask questions.
Hello. All right, this is Ms. Chambers. So what I need you to do is to type your question in the chat window, but don't hit enter until your name is called. So you'll raise your hand when you want to ask a question. Go ahead and type it in the chat window, but don't hit enter until I call on your name. So it looks like you can raise your hands now. Okay. Okay, Sean, you're up. So what would need to be the first steps taken by NASA in determining whether or not Vasistas Borealis is actually an ancient ocean?
Okay, I've got a good answer for that question. When you're looking at an ancient ocean, you want to find features along what you suspect is the barrier or the rim of that ocean that are similar to what we'd see on Earth. We've taken a look with satellite imagery, and we found that there actually are features along the rim of Vasistas Borealis that actually look similar to what we see, say, in the Pacific Ocean. Areas where there was glacial interaction along the edge, and you had, basically ice caps that were moving around in what you would presume would be a large fluid body of water. If we could send a rover to the rim and further investigate those features, that would be a huge advantage. Also, if there's a mission that could actually excavate through the surface a little bit, and if you could go to some of the lowest elevation areas of Vasistas Borealis, then you could look for things that suggest that oceanic crust was there a long time ago. So I would say that there'd just be a need for NASA to realize that there's a good possibility that was an ocean, because once you send something out there, you've paid all that money, then you've kind of committed to that investigation. If it wasn't an ocean, are the alternatives worth the money that you've invested into it? So really, I think the willpower and then investigating the center, investigating the edges will be the key.
All right. Chris, you're next. Oh, sorry, Chelsea. Do rocks have possible compositions on Mars as on Earth? Have we found any rocks or minerals that are completely different from anything we've ever seen here, or we have been able to identify everything in terms of similar rocks and minerals we have on Earth?
So far, I think everything that we've seen on Mars, we have a counterpart on Earth. So we haven't seen anything that's been too different. Actually, when we've looked at things on the moon, we have actually seen things that we don't see on Earth, and we've seen that on asteroids as well. But for the most part, Mars, every mineral we've looked at there has been similar to Earth. But that being said, Mars is a long way away. We haven't done a lot of surface investigation yet, so there's a lot of minerals there that probably are remaining to be found, and there could be some that are not found on Earth.
All right, next, Chris. Could you please provide us with some of the internships or extracurricular activities that you are involved in during school or that you think provides to be beneficial?
Well, it always depends on what type of career that you're interested in. But I'd suggest that no matter what your major is, it's definitely good to talk to your student or education office at school and find out what kind of career opportunities there are, what kind of internship programs there are. I've done geophysics internship programs, Mars geoscience here at NASA, and that just really came from asking my school what's available. And probably one of the most important things is if you know that there's an area of science you're interested in, find professors in that science and ask them, what can you do to help them out? Volunteer for things. You'd be surprised at what volunteering can lead to.
All right, Violetta. Okay, we'll go ahead and go to Aaron. Is there any evidence for geothermal hotspots on Mars in the present or recent past?
Well, what we're looking at today are a number of geysers that we can see, most of which we've determined are a result, like I said before, of carbon ice that is turning into its gas phase, usually as a result of a changing season in Mars, moving to an area where there's more sunlight. And so geysers are being created by the dry ice that's subliming back into gas, and it's bursting, it's putting pressure on the surface. That's not something that you find high temperature in, so it's not something I would describe as geothermal. Now, we haven't investigated every geyser on Mars. There could be geothermal activity, and I know that the NASA InSight mission, which is a lander that's going to specifically send, if you will, a thermometer into the soil of Mars and determine what the temperature gradient is under the surface, that will probably give us a better idea if geothermal activity can even occur. We do know, though, that at least at one point in time, volcanic activity was occurring on Mars, but we don't see any existing volcanic activity. So it's an open question right now.
All right, Violetta, your turn.
I was trying to type, and I don't know if you guys can get my messages from the chat. Okay, my question is, for example, if I'm interested to look for the valley, you were showing that it's located on the north, or you guys cut it in a different way? The map.
If you're looking for the valley, are you talking about Valles Marineris?
Yeah,
the big scar?
Yeah, it was the big valley on the right-hand side on the second.
The big valley, yeah. Yeah,
I'm just
if you
wondering,
look at a Martian... Go ahead.
Is it on the north, so it's going to be kind of difficult to send a rover over there, or it's in the middle of the south, I mean more to the equator? area?
I'll address, if you're talking about Valles Marineris, that's close to the equator. So that's not too far north, and from a temperature and sunlight standpoint, that would be okay. But the terrain's very rough. It's very difficult to send a rover there with the budgets that NASA and other space programs are working with now. Now, if you're referring to Vastistus borealis, that huge, smooth, low elevation, what we may think of as an ocean on the northern part of Mars, there's parts of that are far enough south that they're not a problem with the ice cap being too close. And there's parts that go right up to the ice cap. The ice cap sits in Vastistus borealis. So you can go farther south and you can have a safe mission there. So yes, if that's the one you're referring to, either one, they're far enough south that the pole's not a problem.
All right,
Thank you.
Eric, you're next. Besides the cost and risk involved, what can be learned from ice core samples taken from the northern ice cap of Mars?
I was hoping someone would ask about that. Quite a bit. There's the two polar ice caps on Mars. There's the northern and there's the southern. The southern doesn't change as much as the northern, but they both have something similar. They both have a large area of water ice, real, legitimate, drinkable water ice that is frozen permanently, and then on top of that there is a layer of dry carbon ice, CO2 ice. It's very thick on the southern pole. On the northern pole it's not as thick, and the carbon ice layer actually disappears between seasons. So there in the winter, during the summer it blows off, becomes gas, and creates hurricane-level winds that are coming up off the ice cap. So if you drop a lander there, if you had the ability to, and you did it during, say, the Martian winter, you could actually get a lot of information about how thick that dry ice is, what kind of phase transitions it's experiencing at different parts of the season, and also by knowing that, you would know how easy or tough it is to get to water samples there. And if you drop it down there when the dry ice is not there, you could find out what is the chemistry, the chemical compound presence in the water. Are there other chemical compounds in it? And you could also maybe get an idea how thick it is. That would be very interesting. So, yeah.
All right, next we have Crystal. Would a tin coat be good to play a rover to create a barrier between the surface and the rover, similar to food processing?
You have to think of a couple of things. If your rover is going to be in rough terrain, you definitely want to have metallic alloys that are very, very, very thick, very tough. Even if you look at the photos, you know how the Curiosity rover takes these very well-publicized selfies from time to time? It's starting to look a little rough for wear. There's holes, a lot of holes popping up, parts that are coming off because the terrain's not friendly. So you could put tin on there. If I don't know what the cost would be of putting tin coated alloy on top, but really the main thing is thinking about how affordable it is and how the terrain you're going into is going to interact with the rover itself. You want something tough if you're going to be in an area with elevation change. If you're going to a smooth area, Opportunity and Spirit are great examples. You don't need a real tough rover for those areas, so it would be less of an issue there.
All right, James, it's your turn. How do we know about the interior of Mars, the crust, mantle, core, etc.? Even when the diminished atmosphere on Mars, do you think it's possible to tell what the weather could be in advance, like a Martian 7-day forecast?
Well, that's actually not a bad question. That's something that scientists are very interested in. As far as what we know about the internal structure of Mars, it's just like how we know about the internal structure of Venus, and we've sent almost no spacecraft there. When we use physics to look at the orbits of the planets around the sun, we can determine a bit about the mass of those planets based on how they move, if they have any wobble, what their orbital period is, things of that nature. We can get an idea of the mass. And by doing that, we've determined that Mars has a very low mass, but we also have seen, based on what we think are pieces of the mantle that have hit Earth in the form of meteorites, we've seen what we think the mantle was made out of. So the best picture that we get is that there is some kind of an iron core. It's not as big as Earth. It's relatively small in ratio. There is some sort of semi-fluidic nature there, because if there wasn't, then Mars would have a much heavier mass than what it does for its size. And if it's semi-fluidic, there's only a few minerals that could even be in a fluid state at that area of Mars. So we get a fairly good idea just with some physics, some orbital physics. But missions like InSight, which is going to be sent, and it's going to give us some seismic readings of the internal area of Mars, they'll tell us a lot more, and we'll finally know, is there an iron core, is there not, and how big are the core and mantle. So to answer that question, and then what was the other part of your question? Forecast. So the current instruments on the Curiosity rover are giving us wind patterns. The 2020 rover that has been announced and is going to be launched to Mars in 2020, we're talking about instruments that could do precipitation measurements, wind measurements, and a number of other readings, atmospheric compounds. So we're getting closer to a point where we're going to start to know what exactly is going on with Martian weather, and maybe a 7-day forecast in a small area will be possible. But we'll need a lot more satellites in orbit before we can do something like that on a larger scale.
All right, next we have Virginia. If we could drill farther than what Curiosity is capable of, what would we expect to find? For instance, if we could drill down to 10 meters, what would we think would be at that depth?
10 meters is actually a very aggressive depth to get to when you're doing a planetary mission. And I'm sure that many planetary scientists would be very elated if they could get there. The kind of depths that have been discussed are more in inches than they are in feet or yards or meters. So if you could get to 10 meters, say in Gale Crater where Curiosity is, it would really depend on where you're at. There's parts of the crater that were probably lake for a long time. If you go below a lake bed on Earth, you're going to find there's an awful lot of sediment that you're going to go through. It may not be that interesting. It's in geology terms, it's called mass wasting, meaning that there's just one thick strata of just the same stuff. So you're not getting a lot of interesting stuff. But if you could get onto the Mount Sharp there, and you could do a 10-meter drop in, with a drill on, say, like some of the higher slopes on Mount Sharp, then you might get a lot of interesting information about, whatever period of Mars's history that area of the slope represents. So you got to find the strata, and that you're looking for, and if you go 10 meters, you'll get a lot of information about that period of history. If there were anything like trace fossils that were possible in that area, I think 10 meters would be enough to find something if you went into an area like that.
All right, Ed, you're next. Okay, Priscilla. What kind of affordable materials should a rover be made of to prevent being damaged by the terrain?
Affordable material. The tricky question when you're building a Mars rover and you're looking for metal alloys that are good versus not, or plastics that are good versus not, is that you have such a variety of conditions that rover is going to experience over the timeline of the mission. You have to get the rover there, so it has to be strong enough to withstand all of the things it's going to experience during transit. Curiosity, being a very large, heavy rover, obviously, was literally bounced across the surface. It landed with a giant beanbag, essentially. Other rovers have been airdropped, and it really depends on what method you're looking at. If you're doing an airdrop, you probably don't want anything very heavy. If you're doing something heavy, like we did Curiosity, and you're bouncing across the surface, the fact that it's heavy, depending on if that comes from scientific instruments or from the materials it's made out of, you're going to have a cost there. you can only land so much mass on the planet the way we do now. So if you've got more mass to the materials, then you reduce what you can get in scientific instruments. And so it's a sophisticated budget plan. And since I'm not an accounting major or finance major, I'm going to defer that question for now.
All right, thank you. Mark, you're next. Is the olivine or feldspars located near volcanoes? And are there any volcanoes located near what could be considered the oceanic rim?
Okay. A lot of the olivine deposits that we've looked at so far have not been near what we know were ancient volcanoes. But a little disclaimer, it's a little tough for us to know what all were ancient volcanoes and what weren't. We see a lot of things that some scientists say, well, that was a volcano, but we just can't know because we need more investigation in that area at the surface level. So we do see olivine deposits that are near what some scientists argue were volcanoes. And other scientists say they were not volcanoes. So the ones that we know were definitely volcanoes, we haven't seen olivine deposits around them. We also haven't really looked. If we look at the Vestistus borealis in that area, if you remember the map that I showed you, a lot of it is just an enormous flat plain. Because of how much area of Mars it covers, of course, some of its edges do go close to mountains and to things we do know were volcanoes at one time. If you look, Olympus Mons is in part of Vestistus borealis. There's also another obvious volcano that sits inside of it, but they're not like out in the middle where you would have that volcano erupting and creating this enormous lava plain. So if you're kind of trying to figure out, did volcanoes make that lava plain, we don't have convincing evidence right now.
All right, next, Chris. Earlier you mentioned a valley like a scar through Mars. Are there entrances or passages to the valley floor that a rover could make it after landing nearby?
Valles Marineris is a very deep valley, a very deep canyon. It's also very long. It would be longer than any canyon on Earth today if you were to measure it. And to talk about entrances, if you look at it on the map, the surface around it, the area around it goes into a big steep drop off to get into that valley. At the end of the valley, it empties out into, if Vestistus borealis was an ocean, it would empty out into the sea. It would empty out into the ocean at one end. The other end, it's farther inland, if you think of things in terms of like that on Mars. So it's not like you could drop something sort of nearby and find a nice slope to go down. You're going to have to drop it either right down in the middle, or you're going to have to drop it down where it empties out into, you know, an area that's with Vestistus borealis, and then you could send a rover in. But right now, rovers can't make very fast progress across the surface, so it's not likely that you'll get deep into that canyon from where it empties out. You probably need to airdrop something right into the middle there. And that's still a little tricky. That's still not something that there's a lot of confidence in.
All right, Danielle, you're next. Are there places on Mars where the wind factor wouldn't be as harsh?
Yeah, the equator. The wind factor is the harshest close to the poles because that's where you have the most extreme temperature variations. When the seasons change, that obviously has an impact on wind, but really, when you're close to the equator, the wind is probably at its friendliest. You're not going to get away from the kind of winds that create those little twisters, but like I said, those twisters are not that strong. So if you have a small remote control rover, they may be a big deal. You have something like Curiosity, maybe not so much, but you can't get away from that anywhere on the surface. There's always going to be at least that level of wind.
All right, Ed. What are the dangers we should consider when sending a rover to the polar ends? And can you compare both terrains on the polar ends to something here on Earth?
Actually, a lot of Mars, not just the poles, a lot of Mars is very similar to Antarctica here on Earth. The areas of Mars that are not at the caps are very similar to what is called the dry valleys of Antarctica, so similar that a lot of people go there to train to study Mars. The ice cap that's on Antarctica would be very comparable to the summer ice caps on Mars. I should say the northern summer ice cap on Mars. When the dry ice is in its solid phase, there's probably a lot of conditions there that you would see that would be completely alien to anything that we've ever seen on Earth. Because dry ice, carbon does not sublime on Earth. It doesn't have a phase change from gas to solid and solid to gas. It doesn't happen here. So at least not as a product of the weather. So that has no comparison at all to Earth. But the summer northern ice cap would be similar to the Antarctic ice cap.
Last question is from Josh. What would you expect to find from an investigation of Hallis planitia?
Well, in my personal opinion, it's obvious that Hallis planitia is a big bowl, and at the bottom of that big bowl is probably the lowest elevation that we can obviously see from Mars. You know, barring that there's some canyons or cuts in the surface somewhere that are very deep. If there was ever weather phenomenon on Mars where there was extant rainfall, then the bottom of Hallis planitia would definitely collect moisture and water. So if you were to go to the center of Hallis planitia, in my opinion, you would find evidence of water at the bottom there, and of ancient water if there was ancient water. So I'm not willing to commit and say that there were oceans or seas or anything like that, but there were lakes. We know that Gale Crater had a lake in it. Other craters had lakes in them. Opportunity, which is on another part of Mars, that there were lakes near Opportunity. So I'm pretty certain that you're at least going to find mud cracks under the ground in the center of Hallis planitia. And if there was a sea there, probably would find a lot more interesting features and minerals that are consistent with our ocean's subsurface.
All right. Thank you, Aaron, for your time today. We appreciate you coming and talking about Mars geology. I know we all learned a lot today, so we want to thank you for your time. Oh, yes, and before everyone signs out, we have another webinar scheduled on September 16th from 9 to 10 a.m. Central, and it's going to be on Orion. So you don't want to miss out on that chat. So we hope to see you September 16th for that next chat. And if you want to say anything in the chat window, you can comment to the presenter.
Could you please repeat the time for September 16th
yes,
webinar?
It's September 16th from 9 to 10 a.m. Central.
Thank you so much.
You're welcome. Bye, everyone.
Bye.